Now we'll take a look at different units of concentrations, and once again we'll look at dilutions. You can find to start with density. Density is a property of solution or any liquid, and it's result of division of weight of solution by its volume. So units are kilograms per liter or grams per mil, which is exactly the same. Density of water at 4 degrees Celsius is 1 gram per milliliter with very good precision. 4 digits are 0. There is one more convenient unit if you are using non-metric system. It's specific gravity. It's density divided by density of water at 4 degrees Celsius, which again is 1, of course. But this result is dimensionless, so it does not matter what units you are using for volume and what units you are using for weight. A specific gravity will give you the same number. Well, it's important to remember that 1 liter of water is 1 kilogram, and for diluted aqueous solutions it's true as well. Now, if we look more carefully at densities of water, yes, here we have 4 nines at 4 degrees, so essentially it's 100. With increase of temperature, density going down. Actually, it's going down also with decrease of temperature to 0 Celsius, but not too much. So at practical room temperature, you have deviation of 0.02, which usually we cannot just omit for analytical quality solutions. If you want approximate density, you still can count it as 1. What about practically important solution? At room temperature, 0.1 molar sodium hydroxide will have 1,002 gram per ml, and 0.005 molar sodium hydroxide will have very close to 1 density. 0.1 molar HCl solution has a density of 1 with fantastically good precision. 0.005 will be slightly less dense, still very close to 1. So, concentration units. Very common unit, it's weight percent. Grams of solute in grams of solution per 100. So it corresponds to concentration of 10 grams of solute in 1000 grams of solution, or 10 grams per kilogram. With primitive approximation that density is 1, you can say it's 10 grams per liter. But if you want to be more careful, you need to multiply by density. Next, weight to volume percent concentration. Still useful unit, sometimes we have it. So it's usual percent concentration multiplied by density of your solution. So you have grams per ml multiplied by 100. We also have volume by volume percent concentration, which is common when we talk about liquids. So when you have weight by volume percent concentration, you multiply it by 10 and you have concentration in grams per ml, which to my humble opinion is far more convenient. If you have percent concentration, you can multiply it by density of your solution and multiply by 10 and again receive concentration in grams per ml, a very convenient unit. So example, let's calculate concentration of 38% hydrochloric acid with density of 1.1789 grams per ml at 20 degrees Celsius in grams per liter. So we are taking uh, this very formula, 38% multiplied by density and by 10, we have 448 grams per liter, and next digit is 0 just in case. But a 3-digit number because percentage was 3-digit number. Next very convenient unit is molarity. That's concentration in moles per liter. How many moles are in 1 liter of solution? One more parameter that we need to calculate molarity is formula weight. It's very common abbreviation. Even so, perhaps you need to say formula mass, but formula weight is more common. Same, you'll be saying atomic weight instead of atomic mass. Again, very common abbreviation in practice. So, concentration in moles per liter or molarity will be our concentration in grams per liter divided by formula weight. Alternatively, concentration in grams per liter will be molarity multiplied by formula weight. You can also say that molarity is 10 multiplied by percent concentration and by density and divided by formula weight. If density is 1, it will be 10 by percent concentration divided by formula weight. Again, very convenient. So for example, 1% HCl approximately will take approximate formula weight of 36.5, and our molarity will be 10 divided by 36.5, 0.27 moles. You also can use micrograms per ml or ppm units. In that case, it will be 1000 by ppm divided by formula weight. For example, 10 ppm solution of lead with atomic weight 207.2 will have, of course, very small molarity, 4.82 10 to the negative 5. Let's look at one example. Concentration of sodium chloride solution is 2 grams per liter with uncertainty in third digit equal to 2. Let's calculate molarity of this solution. Formula weight of sodium chloride is 58.443 grams per mole. It's 5-digit number, so we do not need to take into account any uncertainties here. Our molarity will be concentration in grams per liter divided by formula weight. We'll have this result as a 4-digit number. Uncertainty is calculated exactly the same way. You take uncertainty of your starting result and calculate by formula weight. You have this number, and it's 3 in the last digit here. So our result is 0.03422 plus minus 0.403 mole per liter. Or you can write it more concisely in this fashion. 3 is deviation in this last digit. Alternatively, you can calculate concentration in grams per liter if you know molarity. So I have molarity of my sodium hydroxide solution 0.1, 3 zeros, and 2 is uncertainty in last digit. And I want to know a concentration of sodium ions. So I don't care about hydroxide. Atomic weight of sodium is known with fantastic precision, practically infinity for us. Concentration in grams per liter is calculated as molarity multiplied by formula weight. In our case, it's simply atomic weight of sodium. So concentration will be 0.1 by this number. We have 2.299. It's very easy to see, and we retain 4 significant digits. For uncertainty, we do exactly the same. We take uncertainty from this expression and multiply by atomic weight, and we have it's a really small number. So we can write our result using this and this. So 2.299 plus minus 0.005 grams per liter sodium ions. Or more concisely, 2.299 and error is 5 in the last digit, grams per liter sodium. Now quickly, dilution of solutions with molar concentration. Again, number of moles before dilution and number of moles after dilution is exactly the same. And number of moles is equal to volume multiplied by concentration. In each case, number of moles here, volume, concentration, number of moles here, concentration. So volume before multiplied by concentration before is volume after, concentration after, or C1 multiplied by V1, C2, V2. Of course, as we have seen before, it's true for grams per liter. Now it's true for ppms, and it's true for molarity units. Let's look at one example. Again, I have 0.1000 with uncertainty 2 molar HCl solution. I take it by 50 ml class A pipette and place into 500 ml volumetric flask, again class A, and dilute it in this flask to the mark, of course with mixing. So I need to multiply by 50 and divide by 500, which of course is simply division by 10. So my molarity was 0.1, now it's 0.01. This is easy, it's just moving a dot one position. And now what about uncertainty? My starting solution had this uncertainty with this absolute magnitude, so relative uncertainty was 0.02. What's uncertainty of my pipette? Tolerance is 0.05 ml, getting it from the table. So relative uncertainty is 0.01. 500 ml flask has tolerance of 0.2 mL, and relative uncertainty will be this number divided by this number, 0.004. Now, let's just look. These two numbers are much smaller than our starting relative uncertainty. So the only uncertainty that will be of any value will be our starting uncertainty. We retain relative uncertainty, and our starting uncertainty will be simply divided by 10. My result is 0.01, 3 zeros, and 2 is shifted by one position, or 0.010002 look very similar to this. That's proper choice of pipette and proper choice of flask. We retain the starting uncertainty, and our procedure does not affect our precision. What if I would take 5 ml pipette and 50 ml flask? Now situation is slightly more complicated. My starting solution uncertainty is of course exactly the same, but my pipette tolerance now is different because it's different pipette, and relative uncertainty of pipette is 0.02. Same story is with flask. Flask is smaller, so tolerance is different, and this is relative uncertainty. Now, these three numbers are almost of the same value. These are simply equal, so we need to take into account all of them. So total relative uncertainty of our result will be relative uncertainty 1 squared, then relative uncertainty 2 squared, and relative uncertainty 3 squared. So 2 squared 4, 2 squared 4, and 1. It will have 9. Square root of 9 is 3. So our resulting uncertainty will be 0.003. And when we'll multiply it by our result, we'll have such an answer. So instead of 2, we have larger relative uncertainty of 3. Is it bad or good? Depends what you want to do. If you do not need all 3 significant digits, it can be reasonable choice because you are not wasting your solution. You are using 5 mils instead of 50. On the other hand, if you want to use this 50 mils of solution for precise operations, perhaps it was not the best choice. This first procedure was giving us more precise result, and we would prefer to keep it this way in analytical chemistry.